Hello, everybody. And what I'd like to talk to you about this afternoon, evening, this evening, is work that students and I have done looking at a particular kind of geologic deposit, both for the interest of that project in and of itself, and also because it's a good example of the way in which we can use geoscientific methods and geological observations to understand the world in a better way. So the boulder ideas, we'll be talking about boulders, and then this idea that we can decode aspects of the Earth by looking at the rocks of which the Earth is made, right? Earth is made of rocks. It might seem obvious, but we tend to forget it. Everything else is just this like thin little scum of rotted stuff that's sitting on the top, really. So the area that we're going to be looking at is off the coast of Ireland. This is Ireland here, and here in the mouth of Galway Bay you can see a little string of islands. Those are the Aran Islands. Zoom in a little bit closer. This is a European Space Agency satellite image, and there's 3 islands here. You know, the Irish are a race who love language. You all know that. We're great with stories and songs and very rich use of words. These islands are called Inishmore, Inishman, and Inisheer. Inish means island. Inishmore is big island. Inishman is middle island. And Inisheer is Eastern Island, okay? And those are the places that we're going to be looking. Now, along the Atlantic coasts of these islands are these boulder ridges, basically great big mounds of stones. And in this Google Earth image, Google Earth has changed the way we do geology. It's unbelievable. I love Google Earth. But you can see here, this is a section of Inishmore, and north is up. And you can see here this sort of pale gray line. That is the face of one of these boulder ridges. And the scale here, one of these little segments is in or around 150 meters. So you can see that these things are actually sitting here a good ways in from the edge of the ocean. Individual rocks in these ridges are visible in Google Earth, and that blows my mind, right? And I've looked at a lot of rocks in my life. Here is the southwestern tip of Inisheer, which is the smallest of the islands, and up in here you can see a flat surface, and that is one boulder, right? That's about 7.5 meters long. So we can see these rocks from space. And in a number of the pictures I'll show here, you'll see text like this down near the bottom, the base of the ridge, 9 meters AHW above high water. So vertically above the highest point that the highest tide can reach is where the base of these ridges start. And then 80 meters inland, that's 80 meters inland of the high water mark. Okay, so here on Inisheer, the very bottom part of this ridge is 9 meters above high water and 80 meters inland of the high tide. The ridges are quite well organized, they're well structured, and we'll talk a little bit about that. And they contain blocks that are quite enormous. I mentioned that one on Inisheer that's 7.5 meters long. There's a number of very big rocks here. We're going to go in and look at this particular rock right there. Here it is with my lovely husband and son for scale. And large as my husband is, he's dwarfed by this boulder, which is 11.5 meters long. Okay, if your meters, I'm a geologist, I think in metric, if you want to convert to feet, that's, you know, just multiply by 3.3 or approximately 3, right? And this rock here is 78 tons in weight, and it's about 17 meters above high water and 130 meters inland, okay? Non-trivial. Here's another big rock, 43-ton rock, and it's smaller. In fact, I think these two were originally together when they were moved, and this broke and sort of peeled back like that. But just this part of it here is 43 tons. And this one's 220 meters inland. It's a long way. Okay, but can we think about what that might look like? And so I walked out to the sea's edge when I was there looking at this rock. And so that, the blue arrow is showing you that there is the 43-ton block that we were looking at, and I was standing with the ocean to my back here. So it's a heck of a long way. It's a quarter of a kilometer. I mean, it's not trivial. If you go and look at these things, sometimes they look like they've been there for a long time. They're pretty weathered looking. They're covered in lichen. This is a 40-ton block on Inishmore. And others look like they just arrived yesterday. So here's a rock. It's, you know, it's a little baby rock. It's only 3/4 of a ton. If we go in and look at this one a little more closely, you can see that it's got mussels. These black things are mussel shells. There's barnacles here that when you look closely actually still have the little valves on the inside. And this fuzzy-looking stuff is coral weed, a defleshed but a very delicate coralline red alga when it's alive. The flesh is gone, but those very delicate little pieces of hard tissue are still there. So this has not been out of the water for a long time, or these things would have just simply fallen off. Okay, so the question is, so these must have been put here by waves, because there's no mountains inland of this for these to have fallen off of. So the only way to get them where they sit now is by waves, and there's two possibilities. So some people argue that storm waves are doing the work to get these rocks where they currently are, and some of the evidence that's used in support of that is the orientations of the boulders, and we'll talk about that in a little bit, and trapped debris. Some of these boulders will have pieces of plastic jammed in underneath them, or pieces of hawser from ships, or fishing line, things of that sort. Others say no. They say the trapped debris, you guys just think it's trapped there, but in fact it was probably wedged in, shoved in under by a later wave. The boulder orientations, well, we can just ignore that, because basically storm waves couldn't possibly do this work. The waves that you would need, the storm waves you'd need to emplace these are improbably large, and so these must have been deposited by tsunami events. So let's ask the question then, so how much water do you need to move, let's say, a 78-ton rock, like the one I showed you a couple of minutes ago? And so let me walk you through this graph very quickly here. It's just an XY plot, although we've got a logarithmic scale, right? So we go from so off the scale here would be 0.01, 0.1 to 1 to 10. So we're getting very big very quickly. Same here on the x-axis, 1 to 10 to 100 to 1,000. The weight of class in tons here versus the bore height on the platform. That is the thickness of water that you would need moving across the platform in order to move these rocks. So, and you can see from this, from the lines that I've drawn on here, which are simplifications of a large number of calculations and data, that storm waves need more water to move a given height of class, size of class. So if we take our 78-ton rock, okay, so 78 is around here somewhere, that's where it would fall on this line. So a tsunami with about 0.8, about 80 centimeters, 3 feet, give or take, of water on the platform could move that 78-ton rock. Whereas in order to move with a storm wave, we need 8 meters of water on the platform, okay? So, which is a lot of water. Okay, and it turns out you need a much larger wave to produce that. So that seems a little odd. Why should the difference be so large? Why the difference? And so these nice diagrams that were put together a couple of years ago by Gatto try and illustrate that difference. If you think about a storm wave, you have your up and down motion, your wave type motion, and for a storm of any given height here, the amount of force that's being exerted on a boulder by the water that is in that wave is less because it's only exerted for a short period, and then the trough of the wave comes and nothing's happening there, okay? And even when this wave collapses, it produces a bore of water that has a fairly low thickness relative to the height of the wave and just doesn't have the same oomph. A tsunami, which has a much longer wavelength, right? Basically, these tsunamis start coming and then they keep going and they keep going and they keep going. They have much more power. Once they start moving, they've got all the mass of that advancing tsunami behind you to push this boulder. And then the other thing that's in here is that the height of this tsunami is actually the same as this storm wave here. So a given tsunami will actually give you a greater thickness of water on the platform. So a tsunami just really packs a lot more transportation punch, an order of magnitude more transportation punch than a storm wave. And in order to get a reasonable thickness of water on the platform to move a rock, you need a very large storm wave. Okay, so it really does seem that to move these rocks, we need storm waves of a size that would be very unrealistic. We don't expect to be seeing storm waves that are 30 meters high on a regular basis that could collapse to give us the sort of thickness of water that we need. So that's why the tsunamicists say storm waves aren't going to cut it. We don't care what the orientations are. We don't care if it looks like there's trapped debris. It's simply not physically possible. Okay. Why look at this problem on the Aran Islands, which, although I'll show you lots of pictures taken in the sunshine, more commonly tends to look like this, okay? Why would you go and spend your summer there answering this problem, looking at these rocks? And one of the answers is embodied in this. Here is a picture. It's an engraving, a print of an engraving that was made after the event, but the last tsunami that affected the northeastern Atlantic happened in 1755. There was what we think was a magnitude 9 earthquake just off the coast of Portugal near Lisbon. It destroyed the city of Lisbon. It did create a tsunami. We have eyewitness accounts, contemporary accounts of a 3-meter wave impacting the coast in Cork, the southern part of Ireland, associated with that. So the maximum height of that tsunami was about 9 feet, 10 feet or so. And it was in 1755, okay, so remember that date. We get storms all the time, okay, so we're in a system where we have lots of storms, but we haven't had a tsunami in a couple hundred years. So if we can look at these deposits and determine that they are young, then we can eliminate tsunami. There are many places where there are deposits like this, but they're almost all in places where you are tsunami prone as well as storm prone, not in the Aran Islands. The great thing about geology is that if we have these codes that are written in stone, basically, that the processes that happened in the past leave a pattern, leave information in the rocks for us to read, right? These aren't rocks, although actually everything that's in these cars came from the earth and was rock at some point, from the plastic and the metal and all of it. That's another story. This is a picture that was taken after the tsunami in Japan last year. And you can easily see from this that this is showing us that because of the way these cars are stacked, that the tsunami was traveling from your right to your left. Okay, it moved all these cars. You could actually, if you wanted to, interpret little eddies and stuff in the tsunami as in the way in which it scattered and distributed these things, and also that the energy ran out right about here. Okay, and we can use, and so obviously we know about the tsunami, we saw it and all the rest of it, but if that tsunami had happened hundreds of years ago and we could come back and look at these cars, we could recreate the tsunami from these cars. We can recreate the events from the record of the deposits. So we go out and we start looking at these ridges. One of the things about this project that I love, students are central to all of the work that I do. This project is a little unique in that it was also a student-initiated project. I've been working on it now for a number of years, but it was this student here, Danielle Zentner, who got me involved. She read a paper about these rocks that was interesting. She went there one summer on her own initiative and looked at them and came back saying, I want to do a senior thesis on these rocks. Would you advise me? And I'm like, Boulder Ridges? I don't know about Boulder Ridges, but Aran Islands, hey, I'm going, we'll go. And the Geosciences department was able to provide some funding to make this happen, and so off we went. And she wrote her thesis on it, and we've been going on since then. I went back in 2010 with 2 other students, Brian and Nari, was back there last year with Miranda and Dave, and then this year looking at similar sorts of deposits, but on the mainland. With Leif Elliott, who's going to be doing a thesis this year, and Kella John. So this is ongoing, and it all started with this one student's interest and idea, which is fabulous. So what do we do out there? We systematically measure these ridges. And this is a picture of Inishmaan, simply showing the locations, the pattern of records. So these are all GPS locations showing where we made measurements. And we do a bunch of different kinds of measurements. We'd stand on top of the ridge with a surveying compass and measure angles and distances. We'd notice how the student is doing this at the cliff edge, and I'm sort of standing well back taking the photographs. But she's peering over the edge with a laser rangefinder, and she's measuring the height of the cliff. And we use these kinds of data to construct topographic profiles that allow us to quantify the heights of the cliff, of the deposits above sea level, their sizes, their distributions, and so on. So we can be very specific. We go in, and in nasty weather conditions, throw tapes across these ridges, and then the poor students have to measure every single clast that's touched by that tape and measure its X, Y, and Z orientations, the large, intermediate, and small axis, so the size of it and the way it's lying, so we can measure its orientation. So lots and lots of data. And one of the things that comes out of this is that if you look at the imbrication, the stacking directions, like those cars, they align with the regional mean wave direction. And so what you've got here, this is, you know what a bar graph is. This is a bar graph that is simply oriented so that you can read compass directions off of it. So what this is saying is that most of the stacking directions, the domino-like orientations of these boulders, they're mostly tilted towards the southwest. Okay? And if we look at the mean wave approach direction, which is known from numerous weather data, it's that direction. Most of the waves, the storm waves, come from the southwest. Can we date the time the rocks were emplaced? This is key to answering the tsunami versus storm thing, and the answer is yes. In these rocks, sometimes in little holes that they make when they're alive, are the shells of dead bivalves, Hyatella arctica, a burrowing bivalve. We can carbon date these, and this individual is about 1,000 years old. Okay, so some of these things have been here for a long time, but here's a rock. This is another little baby rock, only 80% of a ton, but shells in this rock are less than 50 years old. Okay, so some of these things are very young. If we look at the range of ages from these, so here we have, this is all radiocarbon data, calibrated years before present, where present is defined as 1950, down here, what that corresponds to in years AD up here, and each of these represents a date where the width of it is the error at 1 sigma on the age. Okay, so what this is telling us is we have 2,000 years of activity in these ridges all the way up. There's my less than 50-year-old boulder up there. So some rocks look like they've been there for a long time, and often that's so. Shell data from this particular rock are medieval in age. Okay? But some rocks move more recently. This is the one I was showing you. Clearly that's recent. I went back to have another look at it the following year to see what those shells looked like. So when I went back last year, this is what I found. Right? Now you see it. Now you don't. Okay? And so we went, it's like, okay. We went looking for it, and there it is. It had moved 3.5 meters vertically and 60 meters horizontally, and it was upside down, and it had lost all its shells. But we had measured, I had enough pictures of it, we knew it was the same rock. Lots of examples of these. A block here in 2008 was gone in 2010, and we found it around the corner, and it had left a nice snail trail to show us where it had gone. Here is a picture that was published in 2000, that was taken in 2006 and published in 2010. I realized I had a picture of the same area and that there were all these boulders in this picture, so there, that boulder is not there, okay? So new boulders that have been added. But all of those ones I'm showing you are small. There's that 78-ton block. What evidence do I have that something like that is moving? Okay, the clincher data that give us this answer come from the fact that the Aran Islands are unique. Look at all these stone walls. The Aran Islands are famous for stone walls. Here is a map made in 1839, okay? Here is this headland. Here is that headland there. Let's see, there's this wall here, is that wall there. These guys went out. There's that curvy wall there, it's that one there. There's another curvy wall here, it's that. Every blinking wall they mapped. They mapped every single wall on the darn island. And the other thing that they did is they got it right. So what we can do now is look at Google Earth data, lovely high-resolution orthophotography, put it on top of the old maps, and get an absolutely quantitative match, so that if all the walls line up with each other, right, then any differences at the coast must be real, right? And that's what these maps show. And very quickly, so here is the 19th century map, where these dots represent the endpoints of walls, and these lines represent walls that were there in the 19th century. This is simply the orthophoto of the same area. And this is a synoptic map that shows the two together. So the walls are here. Those are the endpoints. And this is the boulder ridge. Okay? There's an even more dramatic example on southwest of Inishmaan, the 19th century map, endpoints and wall in red all along the coast. There's the modern boulder ridge, the overlay. There's the 19th century wall. Underneath the boulder ridge. Okay? Remember that 78-ton block? It sits right there on top of the location of a 19th century wall. Okay? What is this telling us about boulder emplacement? Well, remember what was the date of the last tsunami? Quiz? Oh, and in unison. We could have put that to music. That's fantastic. 1755. No tsunami since 1755, and yet entire sections of ridge have overridden walls. So storm waves have to be doing this work, right? And this picture that my brother took is a fabulous example of the kinds of ways in which waves can climb these cliffs even on a day that's not particularly stormy. Why does this matter? It matters for a couple of reasons. It matters in first part because we don't really know. What this is telling us is we don't know what storm waves are capable of, okay? We know without a shadow of a doubt that storm waves are moving these ridges. The equations, the physicists say that can't happen. We're like, okay? So we don't know what waves are capable of. We know that they do very strange things sometimes. We get very excited when we see pictures like this after Hurricane Katrina, for example. I think something like this looks a lot more scary, right? A 40-ton block, 11 meters above high water, 90 meters inland, and on top of other rocks. Okay? I don't want to be around for that wave myself. The second reason that this matters is because we want to understand tsunami deposits better. After the big tsunami events of the last several years, we want to be able to go back and decode tsunami histories. We want to go back and look at deposits and say a tsunami did this, or a tsunami couldn't have done that. And so for that reason, we need to really understand what processes can build these sorts of ridges. Okay? These rocks that we're looking at here are tsunami deposits. Tsunamis do tend to deposit huge rocks, but not in ridges. Okay? Tsunamis leave giant, enormous, isolated boulders and not ridges. We think the ridges are emblematic of storm deposits. And so I'll leave you with this. It's one of my favorite quotations from Rachel Carson. The sediments, like these boulder ridges, are a sort of epic poem of the earth. When we are wise enough, perhaps we can read in them all of past history, for all is written here. Thank you.